Welcome to Cost Function in Machine Learning. My name is Richard Kirschner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What is in it for you? We're going to explore what is the need for a cost function. What is a cost function? Cost functions for linear regression, gradient descent for linear regression, and gradient descent for neural networks. This is really the math behind what's going on, and it's important to understand what this cost function is and how it's being used in kind of a high-low guessing game the computer does for solving many of our machine learning problems. The need for cost function comes in a number of points. One of them is that after training our model, we need to see how badly our model is performing. While accuracy function tells us how well our model is performing, they do not provide us with the insight on how to improve them better. And when we're talking about the training process, I'm not talking about you train a model and then you run this on there. We're talking about each time you train the model. The model itself is continually going through iterations and finding a better solution. And hence we need a correctional function, which can help us compute when our model is the most accurate. A cost function is used to measure just how wrong the model is in finding a relation between the input and the output. It tells us how badly our model is behaving, predicting. Consider a robot which is used to stack boxes in a factory. The robot might have to consider certain changeable parameters called variables which influence how it performs. Let's say our robot comes across an obstacle like a rock. The robot might bump into the rock and realize that's not the correct action. It will learn from this, and next time it will learn to avoid rocks. Hence, our machine uses variable to better fit to the data. The outcome of all these obstacles will further optimize our robot and help it perform better. The outcome acts as a cost function which helps us optimize our variable to get the best variables and fit our model. The outcome of all these obstacles will further optimize our robot and help it perform better. The outcome acts as a cost function which helps us optimize our variable to get the best variables and fit our models. So to kind of understand this, we're going to look at a linear regression model and the cost function for linear regression. It uses a straight line to fit the model. This is done using the equation for a straight line as shown. This should look familiar as your Euclidean geometry. You have y equals ax plus b, where a is the slope and b is the intercept. In this case, we'll call it output equals a times input plus b for the intercept. In the equation, we can see there are two entities which can have changeable variables. We have a, which is the slope of the line, and b, which is the intercept on the y-axis. If at first the variables are not properly optimized, we get a line which might not properly fit our model. And you can see this line, as you draw it through the data, might give us a very skewed setup. It might predict one point of data, have a small error on a couple of them, and then a huge error on the other four pieces of data going in. And this is when we start talking about error. We're looking more at numbers than a single on-off obstacle. So it's more regression. You'll think regression numbers if you've seen some of our other videos. So we're looking at the numbers. How can we minimize the error? And as we optimize the values of our model, for some variables, we will get the perfect fit. For our linear regression model, the cost function will be the minimum of the root mean squared error of our model, obtained by subtracting the predicted values from our actual values. Our cost function will be the minimum of these error values. And you can see we have our output y equals a input, you could say a input x, plus b. And so in this case, they just went ahead and left it as output. Well, let's look at the cost function. The cost function j equals 1 over n, so we're summing up all of our outputs to inputs. And it's based on what we predicted it's going to be, so that was the output of our formula, minus the actual value that we're looking for, and we square that. For our linear regression model, the cost function will be the minimum of the root mean squared error for our model, obtained by subtracting the predicted values from the actual values. Our cost function will be the minimum of these error values. when you think of this and you're computing this on a computer, like, my mind's trying to look at this long formula. It's not really that long. Really, you're adding them up one at a time, so that makes it a lot easier. Your data comes in and you say, hey, this is what the answer is, and then it goes back and says, oh, these are what the answer was supposed to be. And then you can compute each line one at a time and easily add them up to get your cost function on there. And when we talk about cost functions, we certainly look at that in the linear regression model, and there's a couple other ways to do a linear regression model. But certainly we want to minimize the error, and we look at a cost function for our neural networks. Neural networks are interesting because they have multiple layers on there, and a neural network is a machine learning algorithm which takes in multiple inputs, runs them through an algorithm, and essentially sums the output of the different algorithms to get a final output. The cost function of a neural network will be the sum of the errors in each layer. This is done by finding the error at each layer first and then summing the individual errors up to get a total error. The cost function of a neural network will be the sum of errors in each layer. This is done by finding the error at each layer first. The error function will depend on the model used at each layer. And that's important to note. If you're working with neural network, it's based on the model used on each layer. So there's a whole other level in here that we're not going to address on neural networks. Maybe I'll mention a little bit when we look at the code down here in just a minute. The below function is for linear regression model. So we have a cost function which equals the sum of the actual minus the predicted. There's our error squared, 1 over the number of observations. So if you have 100 points of data going in and you calculate your actual values minus the predicted values, you have to divide it by 100. That way, when you look at the cost function over the next setup, they're very uniform and you don't end up getting a bias on there. And so we can see here the cost function equals 1 over n times I equals 0 to n of y of I minus mx of I plus b squared. Now, when we're solving this, we have a gradient descent. Gradient descent is an algorithm which is used to optimize the cost function or the error of the model. It is used to find the minimum value of error possible in our model. When you're writing code, this comes up. There isn't a maximize function. If you go into most of like scikit-learn and a lot of the other packages in Python, they have a minimize function, not a maximize function. Because we are expecting that the error will never be unlimited. Your error can go to 0. It can't go to negative infinity. And so you always are looking for the minimum because you know it's not going to be an open-ended formula when you look for that minimum. And so the gradient descent can be visualized as a ball rolling down a hill. In this case, the ball will roll to the lowest point in the hill. This point can be taken as a point where the error is least. For any model, the error will be minimum at one point and will increase again after that. The graph shows the error in a model. And again, this comes off of the fact that we're squaring the error. The best error you can have is 0. But even if you have like a negative error, it gets squared, and so you have it's plus or minus 1. It's not looked at as a negative error and a plus error. It's just how far off are we from the least amount of error. In gradient descent, we find the error in our model for different values of an input variables. You can see here we have our error 1 listed there. This is repeated, and soon we see that the error values keep getting smaller and smaller. This is repeated, and soon we see that the error values keep getting smaller and smaller, and it just keeps going down until you find the bottom of our little downward loop on our errors. And so we can take that, and the error graph for linear regressions is given. This graph is obtained using the cost function j. And you can see the cost function j. This should look familiar now. We have our predict minus our actual squared, and we're summing it up over the total number that we're computing that under. We must reach the lowest point in the graph. This can be done by traversing the graph from any point and moving to the point where the error is lower. Now, I know this is a little repetitive, but this is going to make a sense why we're repeating here in just a minute. So as we keep going down the hill, the small difference between each errors can be attained by differentiating the cost function and subtracting it from the previous gradient descent to move down the slope. So here's our cost function of j, and then we go ahead and try new numbers, and the gradient descent is going to be our difference in those. And that's how we're going to look at finding that new value in there. And if this is, they put it in the the differential of j and the differential of theta. So you have theta j minus alpha times the differential. We're just looking at the differences. Just a fancy way of saying, hey, what's the difference of our last cost function minus the difference of our new cost function? And so you get a gradient descent. The gradient descent full formula looks like this, with the original difference minus the new difference summation. And as we continue to go down, we can continue to compute the differences on there to find our new values. In the above equation, alpha is known as learning rate. It decides how fast we move down the slope. If alpha is large, we take big steps. Now remember, I said we're doing a lot of repeating, that we're going down the slope, and you're going to see why we keep repeating that and where the complications come in. And it's important to note that we have this value in there of alpha. Hey, how far are we going to try on the next number? Are we going to jump way ahead? Are we going to take little steps? And you can see that this happens. We might completely miss the least error point, and our results will not be accurate. So that's one of the dangers of having a very high alpha. And as you go down, if alpha is small, we take small steps, and we may take a very long time to reach the error point and waste computational power to do it. When we're playing with this alpha, we might be talking the difference between 100 iterations and 2,000 iterations when you're talking a large neural network. And suddenly, instead of solving this in the course of an hour, you're looking at days processing time on your computer. So this is a big deal to start understanding how that alpha comes in and understanding your data and how it all fits together. Hence, we need to optimize value for alpha to attain the correct minimum error value. So we want it to go down as quickly as we can without missing where we want to go. For neural networks, each layer will have a cost function, and each cost function will have its own least minimal error value. The error graph for neural networks is shown. And this gets interesting because you're going to see that we have multiple minimal error areas that come out from the neural network. And this is also true even on some of our regular models, are more complex. When you look at a polynomial regression model as opposed to linear, where we're fitting a curve versus a straight line through the data, you start having multiple minimals. And depending on where we start, we can arrive at different value for the minimum error. We need to find the minimum value out of all local minima. And you can see here we have a global minima and then the two local minima. And depending on where we start, we can arrive at different values for the minimum error. We need to find the global minimum value out of all local minima. And this can be a real challenge because if you're looking at just one of those loops, you run into the issue that you don't know whether there's other minima out there, minimal values, and if one of those is the global minimal value. And so this can be quite a challenge when we're programming and writing these, putting together these different models, is finding these different points, especially in a neural network. Again, it's not just a neural network that has that come up. That comes up in a lot of regular solutions in our different regression models. The gradient descent for a neural network is just a differentiation of its cost function. It can be written as gradient descent equals the theta j and then the differential of j over the differential of theta. Cost function j equals 1 over the total number we're going to do, and then you sum up the total number of the differences of the y of I minus mx of I plus b, where m and b is your slope and your intercept of your linear regression model. The difference is we're doing that linear regression model across all the different neural nodes and the different layers, and that's why you're summing them all up on there. And it still looks very similar, but it is done in a larger scale. The gradient descent for a neural network is just the differentiation of its cost function. In the equation, m is the weight of the layer and b is a constant called bias. And you'll see that a lot because like in a neural network you might have each node will have all the nodes from above going into it. So if you have 10 nodes going into it, you have to add all those nodes, and they have a weight, the m value, and then the summation of all those nodes going in, all the values going in from the above layer, then has a bias in there, the bias weight that's added in. And then you get the full, you can see down here we have the gradient descent of the differential of j and the differential of theta equals a total number. And I'm not going to go too detailed on the actual formulas. We'll show that in the code A lot of times these formulas are always being updated. So when you're writing code for this, it's important to know these formulas a little bit. If it comes up, you can understand why it's doing what it is, but there's more than one formula to compute this. And so as you start understanding these different formulas, you can start seeing how they fit and how one works better than another. These are the most basic formulas that are currently used today. And you can see here we form a nice little matrix with the 1 over n of I of 0 minus 2 x of I, y of I minus mx of I plus b. There's our linear regression kind of set up right in the middle of the formula. And then you have that with the 1 over n of I equals 0 minus 2 yi mxi plus b. So you're forming a matrix out of it. So as we continue looking at gradient descent for neural networks, in the following picture we are computing the errors for each layer separately, and to this gradient descent will be applied. We also know that each layer has a weight which is assigned to it. And so we have a total error at the end. And here's those nodes I was talking about. You have your input layer, it goes into a layer of algorithms. You use the error from those algorithms to program each one of those nodes. And one of the things they're not showing here is each input goes to each one of the nodes to sum it. So I guess in this particular image, the sum would be a single node. And then you have your layers. Each layer goes into the lower layer and so forth until you sum them up and you get a total error on the end. The weight will be different for each node in each layer. Consider a node in layer 3. The node will have an output which may differ from the desired output. So layer 3 has our predicted versus our actual wanted output on there. And then we create a weight equals a new weight. As a value of the predicted output depends on the weight applied to the layer, we can tweak it to get the desired output. We can similarly tweak the weight of each node in the layer. We use gradient descent on the cost function to get the best value of the weights, which is a variable in the cost function. Using the corrected values of the outermost layer, we can tweak the weight of the layer before that. This will help us minimize the error in the second last layer too. We keep using the corrected weight of layer to further tweak the weight of the layer before that and get the desired output from the network. This is called back propagation as we move backwards. So to kind of put that more in perspective, you have your output, you have all of your inputs. Maybe it's a picture with 1,000,000 pixels on it and you have 1,000,000 inputs. And it comes out and says it's a cat picture or a dog picture, so you might have just one output. Or maybe you have all your inputs and you're trying to figure out what the next predicted value for the stock market is. You have a number coming out. We look at that error at the very end and we push it back to the layer right before it, and we kind of split it up between all the nodes in that layer. And each one of those nodes computes an error. Then all of those nodes push back their error to the layer before, and so forth. That's what backpropagation is it starts at the end and goes in reverse. So we've actually looked at a lot of stuff here as far as cost functions, and neural networks are probably the most labor intensive as cost functions because you're solving that cost function for each layer and for each node in the layer. They're all working together, so it gets very complicated. But the cost function is the same. We're still looking at the same thing even in a simple linear regression model. So let's go ahead and take a look at a demo on a cost function. And I'm going to do this in Python I'm using the Anaconda Navigator to open up a Jupyter Notebook in Chrome. We'll go up here in our Chrome setup and do a new Python 3. Give it a moment there. And so we're going to be looking at cost function. I'll go ahead and rename that. And let's go ahead and start by just importing our NumPy and our matplot library so we have a little view of what's going on here. And then I have a data set that has just a bunch of random points on it, kind of. And we'll go ahead and just bring that in. This is a simple NumPy load text because we put it as a text file. Probably could have put it as a comma separated file or whatever. And you can see it's just a bunch of pairs of numbers. We have 6, 11, 17, 5, 9, 2, whatever on there. And we can take that list of numbers on there that was pretty much randomly set up on this. And we'll go ahead and plot it so you can see what we're looking at. Run. And I would probably spend a little bit more time on here playing with this to see what the numbers are. These are just random numbers. So don't write too much into them. There's nothing fancy going on here. They do kind of group along a nice line. That's what we're going to look up at this graph. And let me switch this. This is, sometimes we'll do graphs where we put the X's in to make it very clear that these are points on the thing. But let's just do a scatter plot on here. That's all this is. If you looked at the last one we had, we did a plot XY, RX marker size 10. This plot would normally do lines, but we change it to RX and we put a marker size, and that's what gives it the nice little X's. But I like the scatter plot better. So we'll just do a scatter plot. And you can see the values kind of go from 5 to 22.5, 0 to 25 on the y-axis. And if we drew a line through here, which is what we're going to be working with, this line would have a y-intercept, our b number, and our slope m. And we'd want to just fit this with the least amount of error between all this data. And so we're going to go ahead and create, and bear with me on this just for a minute. This part gets just a little confusing here. Oops, I left a t off, theta. We're going to take our theta equals our numpy zeros. We're just going to create a zero array, and it's 2 by 1, so it's just one row that's 2 wide. And our new x, numpy delete points, numpy s 1 to 1, insert new x 0 1 axis equals 1, learning rate equals 0, initial b equals 0, and iterates 1500 times. What this means is that we're going to start with a flat line that equals the x-axis. This is y equals 0 times x plus 0. There's our m, there's our b, there's our slope, there's our intercept. And the learning rate is going to be looking at going 0.01 in its steps to find the minimal error. Now we're not talking, this is the distance between this line, what it predicts, which is going to be very small here on this point. Let me just, there we go. You'll see this point here, here's the distance, because right now we have a flat line. Our flat line, let me just draw that in there for you, goes here, and we look at this, the squared value of this difference here, versus the squared value of this distance here, the squared value of this distance, and we're going to look at all these errors. And so when we look at all this, some of these errors, that is the error we're looking at, is the predicted, which is all going to be 0, so we can just put 0 squared, and the actual. And I actually did this backwards, so the actual would be here, would be y square, y minus 0 squared. So y is our actual output, and then 0 is our predicted output the first time through, because we set everything equal to 0. Usually you guess a little bit more in the first one. I would take, when I write a script on here, it pulls the first 2 data points in. So maybe pull these 2 data in, and it says, okay, here's our line with our first 2 data points. And then it starts looking for, then it goes through and looks for the error on there. But this is fine. We start with 0 on here. And so let's go ahead and load this up. So we have our theta, which is going to track the differences. It starts off with pretty much just a simple 2 points, our first beta and our first slope and our first intercept. And so we need to start putting together a cost function. And again, a lot of this stuff is in your scikit-learning packages to find minimums and stuff like that. And so our cost function goes in here, and it says m equals the length of the points. We're going to look at all our points. Y equals delete points numpy s. So we're going to kind of skip through on looking at the y and how they compare. And we end up with a, let's see, here we go. If we look at next, 1 over 2 times n times numpy dot sum. This is just summing all of these values up for us. And we have our numpy.power, numpy subtract, numpy.x, theta. Numpy is such a powerful array. It's just so fun to play with. It's a little hard to go backwards and dissect this, but this is just our cost function on here. It's what we expected and what we're actually going to get. And so when we come out, we print this, we come out, we look at this, we go, okay, so this has an error of 32. That's what that number is. That's just the first time through. The error is the summation of all those lines to the x-axis on there. And we're going to go ahead and do theta second equals numpy array. And it's going to be the same thing, but we're going to, let me just run this, guessing at a second number based on the first number, and it gets an error of 54. Really, this is telling us, because we're not actually going through the implementation of 0.01. Remember up here, we're going to iterate learning rate of 0.01. We just went in and said, hey, what happens if I take this error up here and I adjust for it based on this error? What do I get? Well, my new error is 54. It actually got worse. That's why you need a gradient descent. When we play high-low, you might look at it and just pick some random huge number. You end up with that kind of return on there. And there's a lot of ways. There's actually a lot of math that can go into this. You might do something where, okay, if this is this error, maybe we would try a value on each side of that error that is a quarter of it. So there's some math in here that they do when they do the optimization in Scikit, which really does a good job zeroing in on this. But to understand it, it's better to go ahead and do an actual gradient descent. And so we're going to go ahead here and do cost history. This is just kind of fun. Equals the numpy zeros iteration. And then we have our theta history, theta second. And so it's going to have our first theta. Oops. Yeah, that's right. Theta history, which we start off by just putting in the number of iterations. It's going to go down. And we're going to have our theta second, which is we're going to start stacking on them and tracking them. And that's really not what we're interested in. We're interested in the cost history. But it's kind of fun to generate these values down here. The cost history is what we're looking at. And we start with iterating through the total number of iterations. That's what we set up above, which was what, 1,500? Yeah, there it is, 1,500. So we're going to go through 1,500 iterations. We're going to do our prediction, which equals numpy dot product x theta second. So right here, we're just creating what we guess the new number is based on, in this case, our theta second is our slope on there. That's why we're doing the dot product, slope and intercept. Theta second, so we create our new theta second minus 1/2 times the learning rate. There's our 0.005 times our x dot t dot product, which is a prediction minus y. Now, this code looks a little confusing. When you're digging through it and you go back, you'll see how the numbers match up. Playing with numpy arrays in itself is a lot of fun, and once you start playing with them, looking at somebody else's code is really hard to do. The guys in the back put this together for me. Building your own code just becomes like a very creative, fun challenge to see how it all fits and how you flip the numbers around. The .t means I'm transposing it in a numpy array, so I'm turning it from columns to rows. And we're just going to take our theta history and our iteration and create a theta history, and then here's our temp cost. This is the one that's really important. It's going to be 1 over 2 times n numpy sum, and then we have our numpy power, numpy subtract, numpy dot, x theta second of y2. So we're looking at the cost of each iteration on there. And this formula comes from here, where we're summing all the different values and finding our error. And then we're adding it onto theta history. And so here is our slope, here is our intercept, and it just keeps guessing for each one of these. And we could look at pieces of the history, and you can see it slowly changes on here. A lot of times I'll do something like this and just look at the end of the data, let's look at the last 20. Run that. And in the last 20, you can see that 6210, 3261, 602, this becomes a 5. A 0 is kind of bouncing back and forth on the slope, and it kind of zeroes into the 630 down here. 629, 630. It gets closer and closer to this one answer on there. But that's not the part we want to look at. The part we want to look at is there we go, is the cost history. We want to take a look. Remember, we're dumping on here our temp cost, and we're just going to keep adding it on to the cost history. So let's go ahead and run that. There we go. And you can see we have a nice curve here. And what you want to notice on this curve, what's really important, one of the things a lot of programs look for would be the elbow. Not as important on this particular graph. And somewhere right around here, we jump from 800 to 1400 with almost no improvement. Look how small this improvement is. A lot of times, this improvement, as you get down to here, is less than the actual error that we have coming off of it. And so when you're looking at statistics, if my error is something like this, here's my error, that means that these values right here supposedly are getting better, but they might not be. So when you have, when you start looking at the craziness of data coming in and how it varies, at some point you cut it off and you say, okay, right here we got to cut it off, and you might actually find an intercept here. Usually though, on the curve like this, I would look around 800 to 1000. Around 1000 you really are just bouncing back and forth between the bottom, and in this size of data, that is way beyond what this size of data would actually be able to predict. And that's why you look at these things. You want to know where your points are, and there's a lot of algorithms to guess where this best spot is. But as far as understanding how we minimize the error, you can see we use a basic setup to do our gradient descent to find the minimal error. Finding that bottom of our, whoops, that's a horrible loop. Finding that bottom of this graph right here, how close can we get to 0? There might be our 0 line. So we've gone through a lot. We went through a quick demo to show you what that looks like and what's going on in that minimize routine, using the most commonly used gradient descent with a linear model. And we talked a little bit about how that fits in with neural networks, pointed out that there's a global and local minimals, all important things to understand when you start looking at minimizing the error. One of the most common used tools to train our models in our machine learning kits. I want to thank you for joining us today at Simplilearn. Again, my name is Richard Kirshner with the Simplilearn team. For more information, please visit www.simplilearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.